So I'm Pierre Vermot. I'm very glad to be able to present my work today to all of you. So the initial plan was simply to come here and present my paper on the gravity observation of NGC 1068. However, between my application for a talk at this conference and today, there has been a new paper on NGC 1068 based on Matisse results, which kind of contradicts my conclusions. So I decided to include a discussion about these differences in my talk. And also, if I have the time, I will try to present you a small experiment that I made on image reconstructions with various UV planes. So let's get started, and I'm going to start by presenting my work, let's say pretending that there has not been a Matisse paper changing the interpretation. So here a first look at the data. So these are classical gravity data with visibility, closure phase, and also coherent spectrum and magnitude. I will come back to that. Here I present two possible images of the source based on this data. So the first one is the reconstructed image with Mira, which has been presented in the collaboration paper. And on the bottom, this is a simple geometrical model that I tried on the data. The point is that we interpret this structure to be more or less a ring-like structure with possibly one edge less luminous than the other. But what I want to present today is a bit different. I think that I followed a different approach, which is kind of interesting. The idea is that instead of performing first an image reconstruction and then trying to analyze this image, I directly mapped the output of a radiative transfer model to the various interferometric observables. So my model is quite simple. It's like a torus-like geometry, which goes up to the sublimation radius of the torus with various geometries, densities, and luminosities that I'm going to compare. So getting the geometry of the structure is not that difficult. With the visibility, we've got the typical scale of the structure. With the closure phase, we've got the asymmetries. What has been very challenging for my model was to reproduce all the spectral variations. So for instance, in the visibility, we can see that there is a strong variation of the visibility according to the spectral channel, which doesn't match the coherent spectrum. So we can somehow tune this by adding a background with the proper spectrum, but then we are limited by the total magnitude because the coherent spectrum plus the background must equal the total magnitude. The point is that all these observables are somehow interconnected, and I couldn't fit each parameter on each observable, let's say the size on the visibility, the density on the closure phase. But I had to fit all the observables simultaneously and explore all the parameter space, So this was quite long in terms of computation, but I think that I managed to come to quite a good result. So here I present on the left each side the observables and the model prediction. So in the paper, I say that I come to a quite fair reproduction of the data. Today, I'm going to be a bit more assertive and say that I come to a very good reproduction of the observables, or at least I challenge anyone to do better. Here, I present my model, the best model that I can find. So the image is here, and the set of best parameters are here. There are two things that I want to highlight to them. So first is that my conclusion is that we are looking at a highly inclined ring. Well, in the middle of face on and edge on, which is kind of surprising because, well, at least I was expecting an edge on disk. And the other parameter that is going to be important today is the extension. So in order to match the observed coherent spectrum, the magnitude, and the slope of the visibility across the spectral channel, I had to put a very high foreground extension, so AV up to 70 or 80. So this is my model, what I presented in the paper. But then came the Matisse paper, which kind of, let's say, killed my paper because the main result of this paper is that the structure that we are observing is not the sublimation ring, but a polar emission. And so, of course, since all my model is based on the assumption that we are looking at the sublimation ring, if these results are true, then my model is. So I know that a lot of the authors of the Matisse paper are here today. I'm a bit outnumbered, I would say, but I'm going to try to defend a little bit my point of view, if that's okay for you. So the first thing that I want to say, I'm pretty sure that we agree that we are looking at the same structure in the K-band and in the L-band. So the flux comes from the same structure. We are not looking at two different objects. And the difference is in the interpretation of the structure, what we consider this structure to be. So I say that this is the sublimation ring, while you say that this is the polar region. So here I made two mock images of our models. So in that case, we see the inner rim of the torus. This would be more my interpretation. While I think that you claim this model, something like that, where what we see is basically the launching site of the wind or of at least the bicone ejected. So I'm going today to present two objections that I would have with your interpretation, and I hope that it can start a discussion about it. So first of all, the hot dust. So I know that my model is a bit bold because I assume that the hot dust is inclined and does not hide the central engine. But somehow I think that your model is even bolder because you claim that we do not see at all the sublimation ring. If I understand correctly the paper, you do not say that there is no sublimation ring, but you say that it is hidden by the torus. And then I don't see how it is possible with, let's say, a reasonable amount of matter, because I proved with my radiative transfer that even with AV equals 70, the sublimation ring was still very visible in the K-band. It was still extremely bright with K equals 8. And so you claim that it is so much absorbed that we do not see it at all, which would require an even bigger extinction than what I propose. And not only in the K-band, but also in the L, M, and even I would say the beginning of the N-band. And so my question is, if you agree that there must be somewhere a sublimation ring, how is it possible to hide it? How much extinction we would need and stuff like that. And I did not find any discussion on this aspect in the paper, while for me, this is something that goes against the intuition that we should be dominated by the hot dust somehow. So this was my first point. The second point is regarding the astrometry. So basically, if I understood correctly, what a strong argument that you have to say that we are not looking at the equatorial ring is that you locate the supermassive black hole just below the structure instead of locating it in the middle of the structure like my model would predict. So there is 10 milliarc seconds between these two positions, and you say that you reach a 3 milliarc seconds relative astrometry between the black hole and the L-band image. And what you did for that is you took the maximum peak in the L-band, associated it to the peak of the N-band, then associated this N-band to the ALMA images, then compared it to the VLBI images, with, for all these steps, a 3 milliarc second resolution, which I think would be overestimated because it is like 4 times smaller than the resolution in the N-band. Plus, there could be some offset between L and N-band, between N-band and ALMA. Even if they look a bit alike, there could be some differences. So I would argue that 3 milliarc seconds is a bit overestimated. It would be more 10, in my opinion, and in which case it would be fully compatible with the models that I proposed. So that would be my 2 points. But I don't have much time, so what I did just briefly, because I found it interesting, was to try to reconstruct these 2 images with various UV planes to see if we are able to distinguish between the 2 situations just by looking at the reconstructed image. So I'm going to go a bit quickly. So this is just with gravity. We cannot really distinguish the 2 situations. This is with Matisse, where we can see the extensions of the jet that start to appear. Then I combined it with a fake aperture mask of the ELT. Well, it kind of improves the reconstruction. Then, considering the name of the conference, I added the sparse aperture masking of the JWST without much improvement. My point is that solely based on the analysis of the image, it's extremely difficult to distinguish between our 2 models. That even if the ELT and the JWST will give improvements, the VLTI will still bring most of the information at this spatial scale, so it will stay competitive for at least a decade, I would say. And well, and that's it. I would like to say, pay attention to image reconstruction, which can be a bit misleading sometimes. We don't get all the information. We have to remember that, I would say. And I'm going to skip on my conclusion because I'm late on time and I just said everything, so it's not necessary to repeat it. And I will take your questions, of course.
Okay, thanks a lot, Pierre. Disagreement between results is the way to make progress. So
I love this situation, I have to say.
Very good.
Funny and interesting, yes.
Violetta or Walter, does anyone of you want to comment to any of the two objections that Pierre made to the Matisse results? Or perhaps while you're thinking, let me just ask one question. You said that an AV of 70 would not be enough to hide the inner hot dust in K-band. But is that really true? I mean, my kind of rough estimate is that the AV in K-band, AV to K-band is something like a factor of 10 to 15.
Yes, so,
so then you would get
AK equals 5. This AV
yeah, but then yeah, but if you had 5 magnitudes of extinction, that would be enough to hide it, right?
Well, how can I say that? Assuming that, let's say 10% of the central luminosity is absorbed by the dust and remitted in the infrared, so kind of, I don't know, a rough estimate, you get a magnitude of the source, which is something like 3 or 4 at the distance of 1068. So now I would say that 5 magnitude of difference between the actual luminosity of the source and what we observed is, well, is the result that I get. Basically, my model over-predicts, always my model over-predicts the luminosity of the torus. And so if I wanted to match the observed magnitude, I need to extinct it by 5 orders of magnitude, something like that.
Okay.
And it stays the most dominant. But in my model, there is no polar emission. So maybe there will be less absorption in the polar emission or stuff like that. But I find AV equals 70, and this is not.
I mean, a very quick comment is that you're probably using the wrong dust model, because the galactic dust extinction model is incorrect.
Okay, but
and I don't know which way that goes, but the actual extinction in the K-band relative to the visual depends on a lot of things. Depends on the amount of carbon, it depends on the amount of iron, depends on the grain sizes, it depends on the olivine to pyroxene ratios. And just saying, 70 magnitudes is 5, you know, all of those numbers are just pulled out of a hat.
Yes, a bit, but I don't think.
And then the other comment is that 3 milliarc seconds is the full fringe size at 3 microns. So that's at least a factor of 3 worse than the normal resolution at 3 microns. And at 10 microns, the full fringe is 10 milliarc seconds. So the normal resolution to a point source is about 3 milliarc seconds. So the overall assumption of 3 milliarc seconds propagated accuracy is not crazy. And 10 milliarc seconds is crazy.
I was expecting these comments on the resolution. So basically, at least from what I understand, you're talking about like this Michelson criterion of resolution where we can go at lambda over 2b.
I'm not using a criterion, I'm just doing fitting and looking at signal to noises and see where the difference between the phases and the closure phases exceed what we measure, and that gets you at the numbers we put in the paper.
Okay, so I'm not
using any external statistical criterion.